Imagine if we could accurately predict and manipulate airflow. We could design aircraft that fly faster, smoother, and more efficiently. Ever pondered why planes can't just fly any faster? As you drift through the pages of an in-flight magazine, you stumble upon the Millennium Prize problems, a collection of 7 unsolved riddles that promise a cool $1 million to the genius who can crack. One of these head-scratchers is the Navier-Stokes equation, a mathematical formula that governs how fluids like water and air flow. For 200 years, scientists have been striving to answer 2 seemingly simple questions about this equation. Do solutions exist, and are they unique? The answer could revolutionize industries, not least of which is aviation. Navier-Stokes equation remains a $1 million question, but could the answer lie in the realm of quantum computing? A tantalizing prospect, and one that's well worth exploring. Imagine having a tool that could simulate the flow of fluids. Well, such a tool does exist, and it's called Computational Fluid Dynamics, or CFD for short. This powerful tool acts as a virtual wind tunnel, allowing us to analyze how fluids, like air or water, interact with objects. Magic behind CFD? The Navier-Stokes equation, a fundamental principle in fluid mechanics that describes how velocity, pressure, temperature, and density are related. Fluid dynamics, one of these tricky pieces is turbulence, a phenomenon that causes fluid flow to become chaotic and unpredictable. Turbulence introduces a new level of complexity to CFD simulations. Because of its unpredictable nature, it's difficult to accurately model turbulence. Can lead to inaccuracies in the simulations, making it harder to understand how fluids will in real-world situations. In the world of CFD, the space of interest, say the wing of an airplane, is divided into a mesh of tiny elements. Each of these elements is governed by the Navier-Stokes equation. By applying this equation to each element, CFD solves for key fluid properties like pressure and velocity. It's like piecing together a complex jigsaw puzzle to form a full picture of how fluids behave. Yet, as with any puzzle, some pieces are trickier than others. So, how do we tackle this challenge? The answer lies in refining our tools and methods. By developing more accurate models and implementing more powerful computational algorithms, we can enhance our ability to simulate turbulence. This would allow us to predict fluid behavior more accurately, leading to more efficient designs and systems. Journey into the realm of computational fluid dynamics is both challenging and exciting. Like diving into a sea of numbers and equations with the promise of discovery and understanding. The challenges it presents, the power of CFD is undeniable. It gives us the ability to explore and understand the world of fluid dynamics from the comfort of our computers. Computational fluid dynamics provides a glimpse into the complexities of fluid dynamics, but how can we overcome the challenges it presents? As we delve deeper into the realm of fluid dynamics and quantum computing, a question arises. How do these seemingly disparate fields intersect? The answer lies in the power of simulation. Let's take a step back and see how these two worlds collide. Quantum computing, with its immense potential, could be the key to unlocking faster air travel. It enables the simulation of fluid flow with a new level of sophistication. This is achieved by encoding fluid properties using qubits, multi-dimensional bits that can store extensive information about fluid properties. We then design custom quantum operations, or gates, to mimic real-world fluid interactions. When applied to our qubits, these gates enable the simulation of the complex behavior of air flowing over a plane's wing. The challenges presented are not insignificant. The complexity of encoding and operations for larger systems are among the hurdles to be overcome. However, potential solutions are on the horizon. Alternative schemes like lattice gas or Boltzmann models are proposed to improve scalability, even though they might introduce potential inaccuracies. Occupation number encoding, while complex for many particles, is another promising scheme. A near-term solution might lie in a hybrid quantum classical model, where we leverage the quantum computer for specific calculations within a classical solver. This approach combines the best of both worlds, harnessing the power of quantum computing while offsetting its current limitations. So, as we stand on the brink of a new era in air travel, we can see how the intersection of quantum computing and fluid dynamics has the potential to answer the question, why can't planes fly faster, and may soon make it a thing of the past. Stay tuned as we explore the future of aerodynamic simulations in our next segment. Imagine confronting the Navier-Stokes equation, the bedrock of fluid dynamics which has stumped mathematicians for centuries. With the advent of quantum computing, we are given a new opportunity to overcome this long-standing challenge. The process begins with encoding fluid properties, using multidimensional bits that can store extensive information about fluid properties. We design custom quantum operations or gates to mimic real-world fluid interactions. When applied to our qubits, these gates enable the simulation of the complex behavior of air flowing over a plane's wing. To estimate the likelihood of specific events like turbulence thresholds, we exploit the principles of superposition and interference through quantum amplitude estimation. Additionally, we use a technique called variational quantum eigensolver to approximate the ground state energy of the system, revealing fluid behaviors and aiding the mitigation of instabilities. However, the complexity of encoding and operations for larger systems presents a challenge. Alternative schemes like lattice gas or Boltzmann models have been proposed to improve scalability, but they might introduce potential inaccuracies. Occupation number encoding, while complex for many particles, is another promising scheme. A near-term solution might lie in a hybrid quantum classical model, where we leverage the quantum computer for specific calculations within a classical solver. This approach combines the best of both worlds, harnessing the power of quantum computing while offsetting its current limitations. Quantum computing, with its immense potential, could be the key to unlocking faster air travel. Now picture this. Instead of being confined to the limitations of computational fluid dynamics, we step into the uncharted realm of quantum computing, where we can simulate fluid flow with a new level of sophistication. With this revolutionary technology, we are on the brink of a new era in air travel, where the question, "Why can't planes fly faster?" may soon become a thing of the past. The journey towards faster air travel is a complex one, filled with challenges and opportunities. As we've explored, our journey starts with the Navier-Stokes equation, an unsolved enigma that holds the key to understanding fluid flow. Alongside this, we've delved into the power of computational fluid dynamics, a tool that allows us to simulate and analyze fluid behavior. But the real game changer lies in the realm of quantum computing, a technology that promises to revolutionize how we approach these complex problems, potentially making aerodynamic simulations more efficient and accurate. Yet, as with any journey, there are hurdles to overcome. Encoding fluid properties, designing custom gates, estimating probabilities, all these tasks become increasingly complex as the system enlarges. But with every challenge comes an opportunity. Hybrid quantum classical models, we can leverage the strengths of both realms. As we continue to push the boundaries of science and technology, the dream of faster air travel is within our grasp. The future is indeed exciting.